everyone. I'm Josh, and this is joint work with Philip Johnson-Freyd. So building deductive verifiers can be quite challenging. And by deductive verifier, I mean a program that takes as input a program annotated with some specification written in a program logic and produces as output a set of logical formulas that it will give to, say, an SMT solver. And these challenges really come from two different sources. There's the actual the fact that you want to make sure that this formula is solvable efficiently by the SMT solver, which involves doing various heuristics and simplifications and so on. And there's the bigger problem, which is the gap between the source logic and the target logic, where you want to write a specification for your program in a nice, expressive source program logic, but SMT solvers support much simpler logics. So a better approach is to use an intermediate verification language, the two most well-known of which are Why3 and Boogie. And the idea here is that you have an intermediate tool which is providing a higher level interface to these solvers, and it is handling all of the translation to these lower level formats like SMT. And it's doing various optimizations and so on. And so for the person who's writing a deductive verifier, they only have to compile their source level program logic to this intermediate logic. And if the intermediate logic is nice and expressive, as we'll see Why3's is, then there might not be such a big gap between these two logics, and the task will be significantly simpler. But how do we know that, I show here on the slide two examples for existing real-world deductive verifier toolchains, Frama-C, which uses Why3 as a backend, and Daphne, which uses Boogie as a backend. But how do we know that these kinds of toolchains are correct? The whole toolchain is doing this very complicated set of transformations from these rich specification logics to simpler SMT. It's spread across multiple different projects. Looking at hundreds of thousands to even millions of lines of code. And if there's problems and if there's bugs in any of these components, then that compromises soundness, where your tool says your program's verified, but in fact, there's a problem. And even if the tools individually themselves are correct, there can still be problems that can creep in at the boundaries if they make, say, different assumptions. But in fact, we can't even state a theorem that says that a toolchain is correct, because a lot of these components in here don't have formal descriptions. So there's an alternate approach to building these tools which addresses these issues called the foundational approach. And this is the approach taken by tools like VST, as we've seen, CakeML, and so on. And the idea here is you formalize the semantics of your program logic in a proof assistant, and you write down a program logic, prove in that same proof assistant, you prove the program logic sound against the semantics, and then you might even connect that to a verified compiler as well to go down to the assembly language level. And if the user wants to prove a program correct, they have to carry out the proofs interactively in the proof assistant in that program logic, maybe with some custom automation or tactics. And you end up with a theorem that says exactly what you're proving about your program, that it's guaranteed to hold according to these semantics. And the only thing you have to trust in this theorem is the proof assistant kernel itself, as well as your formalization of the source language semantics. And you get a typically very expressive logic from this. However, these tools are harder to build and they're harder to use. You can't take advantage of the variety of SMT solver-based automation and the advantages of this intermediate language-based pipeline. And for a user, they need to know how to use a proof assistant. They also need to know how to carry out these proofs in the program logic with this custom automation, which makes these tools inaccessible to non-experts. So what we'd like is to be able to combine these two approaches. In a similar way as we saw with the VST talk, we want to enable both automation and these foundational guarantees. It's not practical, as we've seen, to verify the entire toolchain all at once. But we believe that the crucial ingredient is to verify these intermediate verification languages. And we're looking specifically at Why3. And if we have a verified implementation of Why3, that is a verified compilation from Why3 formulas down to, say, SMT, then the problem of writing a verified deductive verifier is reduced to the problem of writing a verified source program logic to Why3 compilation. And as we'll see in a minute, this Why3 logic is quite expressive, which means, again, that this gap might not be so large, and those proofs will not be nearly as difficult. And a verified implementation of, say, Why3 would help to do for foundational program verifiers what tools like Why3 and Boogie have done for verifiers in general, namely make it much easier to build front ends for a variety of languages because they're doing a lot of the hard work once and for all. But in order to do this, we need a formal semantics for Why3, which before our work did not exist, and in full generality. And so with our work, we give such a formal semantics in Coq, and then we're going to show that it can be useful in developing a future verified version of Why3. I'll note that Boogie, which is a simpler logic that doesn't have a lot of the recursive structures that we're going to see in a moment, has been formalized, but until our work, Why3 had not. So what is Why3? I'm going to give just a brief amount of background here. It has two parts. It has a core logic, which is what we're concerned about, and I'll give more details about that in a minute, as well as an ML-like language built on top with annotations. And some tools that compile to Why3 will directly create terms and formulas in this core logic. Other tools will construct these YML programs. Why3 outputs to and supports about 20 different solvers in the back end, including SMT solvers, proof assistance for more difficult goals, as well as specialized solvers for, say, numerical goals. And the way that this works broadly is that the Why3 will translate these formulas via a series of transformations, which you can think of basically as functions from formulas to formulas. Depending on the exact set of features that a solver supports, the exact transformations will vary. But the idea is that a verified Why3 involves verifying the soundness of these transformations. Why3 is used in lots of verification tools. I show here just some of the more recent and notable ones. OK, so what is Why3's logic? What is the thing that we want to formalize? Well, we start with a classical first-order logic, add things like polymorphism, let and if expressions, and then the real difficulty comes from these recursive structures, where Why3 includes algebraic data types with pattern matching, as well as inductive predicates and recursive functions and predicates, all of which can be mutually recursive. And why does it include these features? Well, the goal is to be as expressive as possible while still allowing automation via translation to SMT solvers. And I'll note that this is broadly similar to the logic found in tools like Daphne and Verifast, also SMT-based, which suggests that this is a reasonable middle ground of the kind of features you want. So our semantics is a denotational one, which means that we interpret Why3 terms and formulas as objects in Coq's logic. Or in other words, we give a model of Why3 in Coq. And how this works, a slight simplification, is we start with a Coq function domain, which maps Why3 types to Coq types. And then under a given valuation, we can define the interpretation of terms and formulas. So a formula becomes interpreted as a Coq proposition, and a Why3 term of type tau will be evaluated as an element of type domain of tau, ignoring polymorphism for the moment. And the core first-order logic is encoded the way that we might expect, where a variable value, to evaluate a variable, we will simply look it up in the valuation. A Why3 and becomes a Coq and, a Why3 for all becomes a Coq for all, and so on. To deal with function and predicate symbols, things start getting a little bit more complicated, where now we have to deal with type substitutions and polymorphism. And to deal with the problem of well-typed function application, where we can have functions of arbitrarily many arguments of some unknown but specified types, we use a nice dependent data structure called heterogeneous lists. Now, as I mentioned before, the real challenge comes from all these recursive structures. And I wanted to highlight a few of the design decisions that we had to make, or that we made through the course of this. I won't be able to get into the details in many cases, but I encourage you to check out the paper if you're interested. So existing descriptions of this logic really specify these recursive structures by stating the conditions that they have to satisfy. So for instance, we might say for the interpretation of an algebraic data type, it has to be the case that the constructors are injective and disjoint and so on. And we want to go further than that. We give explicit constructions of these different objects that satisfy these properties. And to do this, we draw on a wide variety of ideas from classic PL theory. To encode our algebraic data types, we use W types. To encode inductive predicates, we use impredicative encoding. And to encode recursive functions, we use well-founded recursion on a specific predicate over these W types. But the idea is that this approach is highly layered, where the encodings get very, very complex, but a user of the semantics doesn't need to worry about any of that. They only need to know the higher level properties of these recursive structures. And I'll talk about a few examples in a little bit. We also encode things as generically as possible, where with only minor amounts of refactoring, we believe that our encodings of generic algebraic data types and inductive predicates are not unique to Why3 and could be reused in other similar developments. But it's worth noting that when we do things this way, where we give these explicit constructions, these structures interact with each other. And the interactions can get extremely subtle. So for instance, to define these recursive functions and to prove that everything terminates for Coq, We need to reason about the very, very precise interactions between these W-type encodings, the pattern matching, as well as the well-founded relation and the recursive function itself. But once we have all that, we can define completely what it means for Y3 formula to be valid in a given context, which means that it's true under every interpretation that's consistent with all of the previously defined definitions. And we can prove some meta-theorems about the logic, like the fact that it's consistent and the fact that consistent interpretations exist, which means that if I have a list of well-typed Y3 definitions, I can always construct the corresponding Coq object. And it means that we're not accidentally creating vacuous definitions in Y3. So as I mentioned before, the eventual goal of this is to have a verified Y3 implementation. And the way that this works, I show in this diagram at the bottom how Y3 is taking your input formula and applying a series of transformations to it before sending it to a final solver. And so to have a verified implementation, we'd want to show that each of these transformations is sound, either by verifying or by validating that the correctness for an individual input, and composing all of these proofs, perhaps along with a tool like SMT-Coq, which enables sound use of SMT solvers within Coq. And we could compose all those proofs together to have a complete verified implementation. And we wanted to show that our semantics would actually be useful for this purpose, in particular by taking two transformations from Y3 and proving them sound. So those two transformations are, first, the elimination of let bindings, which is a very simple transformation, and it's almost trivial to prove correct. However, it has quite an involved termination argument because it's not structurally recursive. As well as the axiomatization of inductive predicates, where each inductive predicate is replaced with axioms asserting that its constructors are true and the inversion principle holds. And this turns out to be a much more involved proof, relying on the least predicate properties of inductive predicates. However, the important thing is we don't need to reason about our complicated encoding. We only need to reason about those higher level properties in this proof. We also want to evaluate whether our semantics are correct, and as well as whether they're useful. So to do this, we built a proof system on top of the semantics. So we prove all of the familiar and classic natural deduction rules to be sound. And then we built a tactic library as well, where we proved tactics like induction over algebraic data types, unfolding recursive functions, simplifying pattern matches, and so on. And again, all of those proofs, which rely on all these structures, don't rely on the details of the encodings. They rely on the higher level interfaces. And we then use this to prove some lemmas from Y3's standard library about lists and trees to ensure that we can actually prove the types of goals we expect to be able to prove using these semantics. And I give an example here of the lemma that shows that if we have a binary tree and we do an in-order traversal and take the length of the resulting list, it's the same thing as just computing the size of the tree from the beginning. And the key idea here is that we can define all these tactics, we can prove them correct, we can prove these goals in the way that we expect, which gives us confidence that our semantics matches the intended ones, and that we're defining these structures and giving the correct properties, correctly. So to wrap up, we gave a formal semantics in Coq for the logic fragment of Y3, which is this extension of first-order logic with polymorphism and these various recursive structures. In the future, we'd like to extend this work in a couple of directions. So we'd like to continue to verify these transformations to produce a verified Y3 implementation, perhaps, again, with a tool like SMT-Coq. We'd like to extend this to features of Y3 that we haven't yet included, like function types. And we'd like to use a tool like MetaCoq, which would enable us to prove Y3 goals foundationally in Coq, but have more idiomatic proof goals instead of with our deeply embedded proof system from the previous slide. And the key idea that I hope everyone takes away from this talk is that verifying these intermediate verification languages is useful. We have the tools to do it. And this can really, really help us to build these foundationally verified verification tools without sacrificing automation. All of our formalization and our proofs are available at that link here. Thank you all for listening. I'll now take questions.
Thank you very much. Questions? Thank you. In the beginning, you mentioned that you interpret types as Coq values, and there you say you want to do function types. So I'm curious, what is the plan? So the Y3 types become Coq types, or really they're Coq sets.
is to be a little more precise. But I don't think that function types would cause significant problems there because everything is living in set. I don't think we have to deal with universe problems.
You want to map them to coq function types?
Yes.
Okay.
All right. Let's not neglect the online questions. So there's a question about the notion of Why3, assuming that all types are inhabited. Does this show up in your formalization? Does it affect the proof?
So we prove according to the typing. We give it, I didn't talk about this in the talk. We formalize all of Why3's typing rules and give a verified type checker, and we prove that this implies that all Why3 types are inhabited. One of these syntactic Why3 checks is on termination, and on inhabitation, and we prove that that does correspond to the types being inhabited.
All right.
About termination, which you just mentioned accidentally. So how do users of Why3 specify these well-founded measures to indicate termination, and what consequences does this have for your tool?
So right now, the termination check in this formalization is based on structural inclusion of algebraic data types, and that's done automatically. The current Why3 implementation is a little bit more general, where it allows a lexicographic order over these structural inclusion, which is another thing that we plan to implement in the future. But there's no, in the core logic, there's no specification of measure or anything. It's just based on a structural inclusion.
Thanks.
Right.
So you mentioned early in the talk that there already was a formalization of Boogie, and then you concluded with a ambitious agenda to verify Why3 itself, and also use a bunch of other bullet points, including metacoq. Has anything similar been done in Boogie or any other tool?
So there is, the work that I'm familiar with for Boogie is based on producing certificates to validate certain Boogie passes, and that's done in Isabelle. So I don't know if they get all the way to validating all of Boogie's passes, or they just take a few of the key ones. But yeah, that's...
Okay.
Thank you. More questions? Let me quickly insert a question here about the reusability of your approach. You seem to have a lot of generic infrastructure. Do you consider organizing this into a framework for specifying semantics of logics and denotational semantics maybe in general?
Yeah, so that's something that we thought about. As I mentioned, that certain parts of the semantics we believe can be done fairly easily.
Quite a lot. Yeah.
So in particularly the algebraic data type encoding and the inductive predicate encoding, as well as other parts like our heterogeneous lists, where we sort of develop a generic library for that. So yeah, we have considered that as well. Yeah, but we designed things in a way that were supposed to be even overly generic, sort of with that in the back of our minds.
Yeah, nice. All right. If we don't have more questions, let's thank Josh again.